All right. Well, looks to me like we've got an evaluation tomorrow and then again on Thursday because I didn't know what time some people might be leaving on Friday.
Oh yeah, I'm leaving at 2.
Okay.
I think the general thing is 2.
All right. So rather than having that be a distraction, we'll just go ahead and keep this as scheduled. And then Friday, I don't know, I believe next up is dot diagrams. A little more elaborate than what you would have done 2 years ago in physical science. But regardless, what do or may we have questions about?
Like, I feel like we should just keep doing sample problems.
Okay.
On the board, and then once we run into a problem, then we can talk about it.
Yeah, I'm still not great with the quantum numbers.
Okay.
Yeah.
Is there a difference between the quantum numbers and the orbital diagram?
Well, you get the quantum numbers from the orbital diagram.
All right.
So is there a difference? I suppose you could say yes, there is. Okay. Okay, so go ahead and tackle that configuration. Then do the orbital diagram, then we'll do the quantum numbers because I want you to start this in familiar territory. So go ahead and take a couple moments and we'll come back. For the third time, okay, we want you to do the quantum numbers. So to me, maybe it's best if you start in familiar territory with the configuration. Then you do the orbital diagram, which means your arrows pointing up and down, and then finally your quantum numbers come from that orbital diagram. And you really don't have to write out the entire orbital diagram because that would take too long. That's why doing a configuration first would make more sense. All right. So one of the things we said, maybe we'll just throw random numbers up here. This is why, if we did this in maybe more familiar territory, we start out with which noble gas? Not radon, that's too big. Okay, so then that means we're up to which number? Okay, now with your slide rule, okay, and we know that xenon is in which period? The fifth one, and it's in which block? Okay, and then which column? So that tells you where you are at in your slide rule. What comes after 5p6? Okay. Okay. 3, 5, 6, 1. Okay. So now if we're in this familiar territory, can we add these exponents together?
Yes.
Okay. So 13, 27, 29. Well, if it was 30, it would be 84. So if it's 29, it must be 83. So with confidence, can we say that this is correct?
Yes.
Okay. So then, this is the configuration. Then we would go ahead and do the orbital diagram. And notice we said you don't want to do the orbital diagram starting from all the way down here. You're just going to run out of room. Okay? I mean, that's going to extend all the way over here and then maybe another line beneath here. So of everything that we see here, where is the most important part when it comes to the orbital diagram and quantum numbers? So right here, because these were the last electrons to go in. So then I would expect that you know two of the quantum numbers right now.
N is 6 and L is 1.
Correct. Okay? So this is where the N value comes from. And then, okay, what does the S block equal? What does the P block equal?
1,
D?
2.
Okay. See, now you did that, right? Okay.
Question. Will we have this slide? Can we use this slide?
Yes, you can use the slide rule.
On our notes, like the actual like.
You can use the deal that looks like that.
Yeah.
Yes.
Okay.
Okay. So then, again, we said I would expect you to know two of them. You got the N value, you got the L value. So then, how many horizontal lines or subshells is there for the P block?
3.
Okay? Because each one of these can hold how many?
2.
Okay? So then underneath here, we could write 6P. Okay? So the mistake that sometimes usually gets made, and I'm slowly getting better at it, is doing that. I mean, that's not wrong. Okay? But if you like putting your M values in there, you're just going to run out of space. So if you put it down a little further, because we know that M is going to equal to a negative value, what L was, to a positive value. Okay? Which means what is a negative value for L? Okay? What's a positive value? Of course, positive 1, and you have to put that one in the middle. Okay? So then how many electrons entered that 6p sublevel?
3.
Just 3. So then why is that wrong?
You gotta fill the seats on the bus.
Right. You have to follow Hund's rule. That is a vocab term. Hund's rule.
How do you spell
Write that down.
Hunds. Okay?
And what was the definition mean?
Is
Electrons.
this going to be on a problem quiz or
No.
the exam?
The exam.
Okay.
So then, if we know that this is wrong, how do we correct this then?
You move that electron to the plus one. The 2 on the. Yeah,
Okay?
basically.
Okay? So you got to move that to over here. So that's the last one that went in. So that means it has to have a positive value of 1, and it's pointing up. So then S is what value?
Plus 1/2.
Plus 1/2. So even if we just change this by just 1 electron, just 1, do you want to go down 1 or up 1?
Up 1.
Okay? So if we change this to element 84, we don't really have to start over from the beginning. So then this is no longer 6p3, it's what?
64.
Okay? So has N changed?
No.
Has L changed? No. Has M changed?
Yeah.
It's -1.
Yes, because now it's over here. Okay? And then has S changed?
Yeah, it's -1/2.
I guess I didn't need to erase all that, but thought maybe if we, oh jeez.
And it has to be -1.
Okay? There we go. Then, well, what happens if we would have added, or excuse me, subtracted 1? Now we're down to 82. Okay?
So then there'd only be 2.
There'd only be 2 of them in here. Okay? What can we conclude about these top 2?
And they'll be the same.
They're still the same. So then we said we took 2 out. Okay? So then M is no longer 1 or -1. It's what?
0.
It's now 0. And what is S?
+1/2.
+1/2. That's right. So that's what that Pauli exclude. Yes.
So, when you added an electron,
Yes. The only thing that might have been a little confusing is maybe you should put this here instead.
But I thought you were just adding electron.
Yeah.
We changed
Plus
the
one
elements so that
charge.
there'd be another.
Yes. That's why we said you need to change the element too.
But what would you do if it had like a plus one charge? On element
Oh,
3?
okay. Well, that's one of the things that can happen with lead, but you'd have to have the Bohr model for that. That would make a little more sense, which we can do just for all practical purposes. It takes a little bit of time. But-
Wouldn't you just have to put like one more on those lines? One more electron?
Like, does the charge change the quantum numbers at all?
Yes. Yes, it
Because
does.
if you would have, if you would add a negative charge instead of,
Then when you're talking about adding or subtracting electrons, the best way to see that is on the Bohr model. And maybe you don't want to go that big as far as this is concerned. Maybe, maybe not. Because we've probably done it before.
Okay.
Is that something that you want to see? Yes? No?
yes.
Okay. So we're doing lead. Okay. Again, the reason you have the Afabo principle and or the slide rule, which means electrons enter the energy level or orbital that is able to receive it. Okay? All right. Is this something you want to do on yourself or talk together our way through it?
If we just go fast.
If we talk it through quick, then.
Okay? So, and this is where we say, follow your slide rule. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and eventually it does get to be a little more difficult. So 4p6, 5s2, 4d10, 5p6, then we do 6s2, then we got to go back down here to 14, and then I think we do 5d10.
6, 2.
Right. And that looks right. Okay? Now, when we're saying adding or subtracting electrons, the best way to see that is with this Bohr model. Because when you look in lead's box, okay, what type of oxidation states or charges does lead have? Positive or negative?
Positive.
Okay, and what are those two charges?
4 and 2.
Okay, so these were the last set of electrons that went in. Okay, so since these are in the outer energy level, we know that right now we've got 82 positive charges. How many negative charges do we have right now?
82.
Okay. What happens when you add those two together?
You get 0.
We're going to get a charge of 0. Okay? Well, since these are in the far outer energy level, if you take these two out of there, which is how lead probably reacts, which one of these two numbers have we changed?
The bottom one.
The bottom one, because these are your electrons. That's what determines an element's reactivity. So we could conclude, how many electrons do we have out here now?
80.
Okay, which means, is it 2 less or 2 more than the protons?
2 left.
2 less.
Okay, so we have an overabundance of positive or negative charges.
Positive.
Okay, and that difference is total of positive what?
2.
And that's one of lead's oxidation states, correct?
Still, box the 2 up top.
Well,
Box.
we usually only do that when it's neutral. I think that's a good way of looking at it.
All right.
Okay? Now, what other charge can lead form?
4.
Okay? Well, it makes sense that we take these two out of here Well, what happens if you take both of them out of there?
That would be a plus one charge.
That energy level is still there, but we didn't just remove 2, we removed how many?
4,
So it's not 80 anymore, it is
78.
78. So now that's not plus 2, it's plus. Right. And sometimes
Do you have to leave that energy level there too then?
because it's still there, right? And probably some of the feedback I'm getting, I don't know how much time you'll even spend with the Bohr model in college, because as science continues to move forward, really a lot of these electrons, these are jumping energy levels, okay? Nothing is certain, but I know in a ground state, if you just leave this lead alone, this is probably pretty accurate. But once you start reacting that with something, strange things are going to start to happen because you're probably adding energy. So these electrons kind of jump around a little bit, and but this gives you a good sense on how and why these elements form charges. Okay, which is why we had said this quite a while ago. Okay, it's fairly common to look at this because you can formulate some of these presumptions, and this is a big part of general chemistry probably when you take in college, is oxidation and reduction reactions. Because right now we can presume that this has a charge of 0, this also has a charge of 0. And it's with the Bohr model that will tell you what's actually happening. Can we erase this?
Yeah.
Okay? So you don't have to write this down because this doesn't pertain to anything. The only thing that we're doing this for is so you can see how and why this Bohr model is what we consider so important for our purposes. Okay? Because if we look at potassium, we know we've got this. Okay? You've got 12, 18, 19. Okay? So then this is what chapter 6 would be like a little further down the road. What would the electron dot diagram look like for this?
So you'd have
How many valence electrons does it have?
1.
And there it is. Right there. Okay? So then what do you suppose you can conclude from chlorine then?
It has valence electrons.
How do we figure that out without using the pole?
Whoopsie daisies.
How can you figure out what?
How many valence electrons it has without
It's the last. It's the electrons on the last
slide?
energy level.
Okay?
Well, what if you didn't do
The column it's in.
Yeah, it's in the 7th column. Yep. So then what is it that chlorine has for valence electrons?
7.
So then would it be fair to say that one of the things that you do in this ionic bond is that now, okay, right here, this has lost an electron. So that must mean this has a what charge?
-1. +1.
Plus 1. Okay? This gained that electron from the potassium.
-1.
So that has a -1. Do these charges add up to 0?
Yes, sir.
They do. So something is happening from this side of the reaction to the other. This has lost an electron. So when that happens, we call that oxidation.
And then what's called reduction?
And the other one is called reduction.
No way.
Okay? Because there's many different ways you can look at this. Which number is bigger, 0 or -1?
Large 0.
Right. So then what happened is, if something is reduced, did the charge get smaller?
Yeah.
Yes, it did. That's one way you can perceive. Everyone's going to have their own way of trying to look at what oxidation reduction reactions are like. To me, when we look at this Bohr model, I think is so useful for that and explains the dot diagram that this lost an electron. So since it did that, now it's got one more proton than electron. And that's what explains these oxidations and reductions. But that's not what we're doing now. But I think we can certainly see it's correlated to this. All right. Anything else that you would like to explore and or look at? Because on page 111, okay, we call it the slide rule, but technically it's called the Afabu principle, which means an electron occupies the lowest energy orbital that can receive it. Okay? That is yes.
What about like Avogadro's number? Would that be yes too?
No. That's just how many molecules or atoms are in a mole.
Well, I didn't.
Okay? Then
How do you spell Afabu?
It's not in there.
AUFBAU.
That wasn't even close.
Okay? Then Hund's rule. Well, that's on page 112. HUND apostrophe S or just S. HUNDS. Orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. So what that means then, we can just do chlorine very quickly. Okay? So we know that it's in the third energy level. So N is going to be what?
3.
Okay? Then we know that it's in the P block because we have 5 here. And that L is what?
1.
Okay? So then here we're going to apply Hund's rule or the bus seat rule, which means that M is equal to a positive or negative value of whatever L was. So that's -1, 0, or +1. So then what Hund's rule says is orbitals of equal energy are each occupied by one electron before any orbitals occupied by a second electron. So these, like we said, are your bus seats. So we're going to do 7 of them, right? 5 plus 2. Okay?
We
No,
don't
you
have
do 5.
enough spots.
We don't have enough spots. Okay?
So you only do 5.
You're only going to do 5. That's another reason to have that. Okay? So you have to follow Hund's rule here that each orbital has to be occupied by an electron before you start pairing them up, before a second electron can enter. There we go. So M has what value? Gesundheit. 0. So then S equals?
-1S.
Right.
So Hund's rule and Afabu are vocab. What else are?
Okay. S block, P block, D block, F block. Okay. The Pauli exclusion principle, that is another one. That is no element can have the same 4 quantum numbers. That's why we had alternated.
How do you spell that?
Okay. What are we doing back there? Okay. Pauli.
Wait, Pauli.
Yep. Then exclusion. EXCLUSION. Then principle. That's also on page 112. Okay. All right. We are slowly running short on time, I suppose you could say. Anything else you'd like to add? Otherwise, that's all we have for today.
Bonus questions? Oh wait, no, we were probably just asking you one of them.
Or 2 days from now.
Yeah, Wednesday. Never mind.
Okay. All right. If there's nothing else, that's all we have. We'll catch up to you next time.